All right, looks like everything is set up. I think we'll give Kian some like five minutes thereabouts, and just kind of like give him some time to catch up. Um, video is paused, as you can see. Yeah, just yeah, we'll just give Kian like 4 or 5 minutes. Just give him some time to join while I figure out the rest of my infrastructure here. Man, it's so hard to host online YouTube. All right. So yeah, if you're also like me, maybe not exactly like me, but maybe like me in that you're kind of excited about the presentation that Gav gave, or maybe you just know you should be excited, but you don't know why you should be excited, because you're maybe not exactly a developer, or you're not exactly a Polkadot core dev. This stream, we will basically watch the video, the same video that I think that everyone has access to. We'll watch it live. At every point in time, we'll probably pause. Every time we get our brains blown, we'll pause. We'll take a minute to digest it. We'll try to break it down for everyone else on the stream. Of course, this video will be recorded, and we'll probably edit it properly and have it available later on for anyone who wants to also watch this. And if you're joining us at home, you can say hi in the chat. I can see the YouTube chat, maybe not Twitter chat, but it is what it is. I really can't figure that out. But if you're on YouTube, you can say hi, and we will be starting shortly. I think just give me like 4 more minutes. But yeah, I just wanted to say that I don't really expect a lot of people would kind of understand that presentation, because it was just too abstract, and I was kind of afraid that a lot of people would be confused. And I've been talking to a lot of people, and I was right. A lot of people are confused strongly by that talk. They don't seem to understand what it means. What is a jam chain? What's the jam toaster? Is there going to be a jam microwave? All these questions flying around. And I'll try my best to also break it down. There's also a few things that I will not, I'll be very, very honest with you. I'm not completely an expert on. I can speak to the best of my abilities on sort of what they mean. And honestly, it's just, this should be fun. I feel like this should be fun. So feel free to leave comments in the chat. Feel free to leave questions, and I'll also try to get to them as well. Yeah, so just gonna quickly check in on Kian and see if he's still coming. Maybe he thought I meant 3 p.m. his time, because it's 4 p.m. my time. Oh, hey, Kian's here.
Hi.
Yo, so we're live actually. I can hear you as well.
Okay,
so
cool.
we're live.
Continue.
We're just gonna start the video, watch the video, right? So I was gonna describe the format a bit. We'll just watch the video. At any point in time, you can ask me to pause the video, and I also pause the video as well, and we can just sort of digest what Gav says and sort of try to interpret it to the best of our abilities, right? So yeah, let's get started, I guess.
Yeah, sounds good.
Yeah. Right. Good. Right. So today's talk is an update on what we've been working on in what might be termed the sort of research and development arm of Parity. And the sort of code name for the project is Jam. You probably know this, or well, you possibly know this from an RFC that I opened 6 months ago called
I never read the
Corejam.
RFC, by the way.
And what I want to do is just give you, make it clear exactly what Jam is and what it does and why we're doing it. Hands up if you already know something about this. Do you maybe read the RFC, or you've seen another talk, or whatever? Right? Okay, like 5 people. So good. For most of you, this will be new. That's sort of good. There are elements of this that I'm giving, telling you about because it's fun and it's interesting, even if it doesn't actually directly affect what you're doing. And there are other elements that actually do directly affect what you are doing, probably. And so I'll point these ones out with sort of a big asterisk, so you know to be like listening. But the other bits you can kind of just like go ooh and ah if you like. All right. Jam. It stands for Join Accumulate Machine. It actually comes, as I mentioned before, it comes from Corejam, collect, refine, join, accumulate. That's the computation model that the machine implements. It's shortened to Jam for a couple of reasons. One of them is that the actual chain itself only does the join accumulate bit. The collect and refine stuff happens off chain. So it kind of works.
Maybe we should pause. Maybe we should pause here. So we have some preliminary details about Jam. There's a lot of operations. There's collect, there's refine, accumulate. But Gav is saying here that refine is only refine and accumulate are the only things that are done on chain. The collect bit is done off chain, right? Which I think is interesting, right? Which I think is very interesting because this already seems very similar to what Polkadot is today, right? Where parachains kind of produce blocks, and that's collected by the validators that are assigned to their cluster, and the validators sort of attest to the results of that block on chain. Or what do you think, Jan?
Yeah, I haven't also thought about the collect part now that I already watched this. I watched the video once, but not with my full attention. And this morning I was actually watching it again, which is why I was also interested when you said let's do like a watch stream or something. I haven't thought about the collect part, but I guess you're right in that it refers to what nowadays parachain collators do, and it's not up to Polkadot to decide that. That happens at some point. I mostly have delved into what refine and accumulate mean. I think the protocol mostly cares about those two, as in those are the main two things that happen on chain, or it's part of the protocol. I'm not even sure anymore, to be honest. What does join mean here?
Yeah, I mean, he goes. I think he goes deeper into it as the talk progresses. But I thought that was very interesting. That was the first thing he said. He gave this clear distinction between what happens on chain and what happens off chain. So collect, refine, off chain, join, accumulate, on chain. It's a good mental picture to sort of hold going forward, and then we'll continue.
Yeah, but maybe I can add already something else. I think one of the things I remember from the RFC, which I read parts of it ages ago, I think when it first came out, was that Polkadot, this RFC is introducing two concepts. So right now we have on-chain and off-chain, but this is now introducing a middle ground where we call the on-chain part remains, but there's something in between that we call on-core or in-core or something. And this really comes back. If you go to the RFC, I think this should still be there. And it goes back to the fact that, when you think about it, it kind of makes sense in the sense that Polkadot is as far as I know, the only properly sharded blockchain, and that it does execution sharding as well. So there is really two different types of workload that you can give to Polkadot. One is something that everyone does. That's on-chain. That's what we call on-chain. That's what all blockchains do. If I want to send some money to you, Sean, for example, everyone re-verifies that. Whereas in a sharded blockchain like Polkadot, when I do that now, when I do the same transfer to you on a parachain, only a subset of validators re-execute that, unless if there's some security stuff going on. And that's what we call on-core. Like it's on chain, but it's not everyone's doing it. And I think this is all like, let's say in the past, or things that we already know of about Polkadot. Again, it goes back really, in my opinion, to the execution sharding detail. So you have on-chain, you have on-core, and then you have off-chain. So collection happens off-chain, whatever, like some collators do it. Then, for example, in the case of one parachain, the execution logic of that parachain happens on core, meaning that the subset of validators re-execute it. And something like the update of the state root of that parachain then is something that happens on chain, as in then every other validator in the system observes it. And if I remember correctly, refine happens on core, and then accumulate happens on chain when we look at the rest of this talk. Sorry, that was a bit long-winded, but hopefully that makes sense.
I think it makes a lot of sense, in fact, especially the on-core distinction. And I think you're right. Yes, refine is done by the validators who are assigned to a specific parachain. All right, let's get back into it. This is it's a really fun video, honestly.
It's also a little bit shorter and therefore faster to type. And it works quite well with the machine thing at the end, which is what it is at the end of the day. It's a possible direction for Polkadot. I'm hesitant to say it's the direction. That's not really for me to say exactly, but I'll come to how I see this sort of rolling out at the end of the talk. So for now, we'll just say it's a candidate design for what would follow on from the relay chain. Now, if you were here yesterday, you'll know that I sort of said I expect this to be a sort of a singular upgrade rather than a iterative thing that we've been doing at the moment. There's a few reasons behind this. One of them is that there are only certain things that you can do with a sort of big bang upgrade that you can't do with an iterative approach. Like, for example, restrict precisely what can be done after the upgrade. I'll get onto that a little bit later.
Maybe we can discuss this upgrade path kind of as well. I remember Ethereum, especially because I follow a lot of what Vitalik writes, and there was a blog post where Vitalik mentioned that, in an ideal world, they would completely remove, the EVM and just have it be only able to verify, ZK proofs of ZK rollups, right? Like, and that sort of stuff, you can't roll it out progressively, right? It'll just have to be this like mega hard fork, and like everything is broken if you were, trying to deploy applications that would just no longer work, right? And I guess that's kind of the same thing in here as well, because this would essentially remove everything on chain that Polkadot does, and I guess shift all of that down to the parachains.
Yeah, it's I don't know. I don't. It's a bit beyond me to like comment on this, as in like I know very little about this jam chain to have a like really well formed opinion, but high level, given that like I know enough to say it's a different chain. Like you just compare this jam chain from what we know so far from this talk compared to the Polkadot relay chain as it is right now, it's a different chain. So it's really kind of makes sense to you do like a one-off big transition where you stop that one and start this one. And I don't know how exactly the logistics of it work, but I'm sure it's possible. And if anything, it's more like we need to take a step backwards, not forward, and then be like, go restudy again. Okay, how do we do hard forks and stuff again? Like things that we haven't really done in the last few years.
And like Polkadot's not really designed to hard fork, if I understand correctly as well.
I mean, but it's there. I don't think there's any like design considerations for hard fork. I guess like any blockchain is hard forkable, I guess. But this is also like beyond my domain of expertise, as in I've only worked on Polkadot and substrates, and before that I don't have a lot of like first-hand experience in these kind of things. But from my theoretical knowledge, I think there's I mean it's as hard forkable as any other blockchain is out there.
Yeah, sure. I mean, but just maybe not our social layer, in terms of like, for instance, look at Beefy. Beefy is like a very critical component of Polkadot, and in that if we had Beefy, we would have bridges, and we would have liquidity, and we would have users, right? But like that has kind of taken a long time to just get validators to, in a sense, hard fork, right? Like, because it could be seen kind of as a hard fork. So maybe our social layer is what I mean. Is not designed for.
I see.
That sort of hard.
Yeah, that makes sense. Yeah, that makes sense. In that I think Polkadot node operators kind of gotten spoiled maybe over the years, that we just
very
generally
lazy.
Can, as in like they generally know, okay, I mean, it's not critical for me to upgrade at a certain time. I'll do it at my own pace. But yeah, this will be a one-off operation that really needs to happen in a coordinated way, similar to the Beefy one.
Yeah, hopefully we get that right. All right, let's get back to the video.
Another reason, and I think maybe a more salient one for this audience, is to try and avoid this constant drip of minor upgrade after minor upgrade, breaking change after breaking change every week or two or a month. This is obviously going to be a bit of a breaking change. Hopefully, we'll try and minimize that to the a very manageable bit of a breaking change. But better to have one breaking change than 5 marginally smaller breaking changes at various times throughout a year or two. It's a new concept of a blockchain. It takes quite a lot of concepts that have been floating around, but it brings them all together, and I think it does it in a way that hasn't really been done before. We might call it a domain-specific chain, sort of maybe that's a more general thing for an app chain, like the domain-specific chain, a chain that handles one particular domain of problems. In this case, roll-ups, what Ethereum folk might call optimistic roll-ups, but roll-ups that are heavily bounded in terms of their security, something that most of these things are not. And in reality, this is what Polkadot has been doing for the last, I don't know, whatever, 4 years, 5 years. It is a roll-up chain. It's just disguised as a parachain hosted chain, but in reality, the relay is already a highly domain-specific roll-up chain. It's just got a little bit more opinionation than we want, and that's essentially what Jam here fixes. Now, there's a bunch of other things, but what I'm going to do is, rather than talk about them in this one big, slide, I'm going to split them out into lots of smaller slides so we can talk a little bit more about each one. Okay, so the Jam concept. Right, it's a domain-specific chain.
Can I
okay.
comment on something?
So it does one.
Actually, it's a question I wanted to throw to you, Sean, because I haven't heard your take on it. How would you describe Polkadot's similarity to, let's say, Ethereum in terms of rollups? I think this is an interesting conversation that I've had with many people. Yeah, what are if Ethereum is doing optimistic rollup, what is it that Polkadot is doing? You're mute.
Right. So I was saying that I was actually going to quote Rob on this, and Rob has a very good description of this. It says, "Not an optimistic chain, not a ZK chain, but a third secret thing." And really, it's a secret thing because not a lot of people can say exactly how Polkadot parachains work, and I guess it's a good chance to sort of demystify that before we even get into the fundamentals of Jam. So how I would describe a parachain is it's an optimistic rollup that can be checked by its base layer, right? So Ethereum doesn't check its rollups. But imagine if Ethereum could asynchronously check what are the outputs. I mean, because if you think about a rollup, it has its own state. It posts the commitment to that state to the base layer. the base layer can be, you know, agnostic of this and kind of just not care at all, and that kind of manifests as a very high finality latency for those commitments in terms of bridging and in terms of like interoperability, either with other rollups or with the base layer. But in this case, it's the case that Polkadot guarantees those state commitments, right? And if they're invalid, it has a protocol that will kick in and reject those state commitments. Is kind of how I think about it.
Yeah, I think honestly, I think this conversation deserves like a full hour to itself. It's a pity that we kind of have to keep it limited. But I think it's an underrated thing. I thought, like, I mean, truthfully, I don't know the depth of like all the rollup systems as well, but I think it's, I agree with everything you said. And I would phrase it like maybe like pessimistic rollup, even though it's a bit of a, I mean, pessimistic is a strange word, but it is kind of true in that, like, I guess like optimistic rollups. This is an analogy that we talked about at some point with some PBA students, and I think Sean was also there. That was a good conversation around that. That optimistic rollups is like you go into a room where all the validators are, and you just stand there waiting to see if someone claims that there was a fraud anywhere. Just like you're in that room and you're like, okay, everyone's silent, then probably it's good. Polkadot is like you go in the same room and you're like, validator number 1, do you agree? Do you agree? And you ask a few people, and then folks at Web3 have done the magic there, let's say, to prove that if enough number of like 3-4 validators already testify that yes, everything was correct, and the rest can check it later, you already get like, I don't know, 99.99% guarantee that everything is final and you don't need to wait much further. But yeah, this deserves a long conversation for itself, but I guess we can keep it limited for now. But it's good that we touched on it, and I think it's important for people to consider and talk more about this, how Polkadot is similar to a rollup chain, maybe just done differently, or devil's advocate done properly.
Yeah, I think like the rollups, they're just like optimistic, but like an enshrined fraud prover in the consensus layer. So it's like optimistic rollup, but the fraud prover comes out of the box with the system. Like, you know, like in Ethereum, each rollup has to design their own fraud prover and everything. But the Polkadot is, it automatically comes with the box. So it just works.
Yeah.
So you do anything wrong, there's a fraud prover checking you asynchronously. So yeah, like nature. That's how I see it.
Yeah, makes sense. I was going to add one more thing, which I think is also kind of required for the viewing of the video, which is that Polkadot will actually stall finality until it has hard guarantees that a rollup's output is final. So, you know, this is actually why Rob, he changed his name to Async Rob, is that Polkadot's finality is asynchronous, and its predicate, you know, the predicate for that finality is the validity of the parachains or rollups that live on top of Polkadot. And I think we've seen events where finality was stalled on Polkadot just because there wasn't, maybe I think it was a malicious block was posted on Kusama, and it kicked off the dispute game, and basically finality stalled for around an hour before finality picked back up.
Yeah. I mean, yeah, all in all, like Polkadot treats rollups more as a first-class citizen. Also makes sense in that like it was designed for parachains, aka these rollups, whereas for Ethereum, it's being sort of like retrofitted. So yeah, there's trade-offs there.
Let's get back to the video.
Yep.
One particular thing, it's not a general purpose chain. In many respects, when you see the jam chain sort of specified, you can see there's quite a lot of similarity to a smart contract chain. In particular, the jam chain allows code to be hosts permissionless code actually on the chain itself. Very similar to what a smart contract chain does. It's not a smart contract chain, though, for a number of reasons. But it's quite nice that it has some of these properties, and it allows us to make direct comparisons for some things. Okay, why is it not a smart contract? Well, actually, I'm gonna wait until the next slide to dive into that. Specifically, what the jam chain does is it accepts outputs of rollups, right? Of bits of computation that have been done already. So these bits of computation are done elsewhere, and then whatever data they yield is fed into the jam chain. The jam chain's job is to essentially provide the necessary apparatus to ensure that this output correctly reflects the input when it goes through whatever transformation it's meant to have gone through. Okay. Again, this is like fairly basic stuff for what rollups are. And furthermore, and probably most importantly, or more, at least as importantly, the jam chain is there to integrate the outputs of these computations into some shared state. Right, so it provides this model, the shared state model for integrating outputs together. This is relatively, we can see how if you compare what Polkadot is doing now, the relay chain, we can see how it fits into this model. But interestingly, we can see how other chains, like what Ethereum is doing, also fit into this model. It's a very general model. In the jam chain, we call we arrange the state of the jam chain into different encapsulations and encapsulated components. A little bit like smart contracts. This is one of the similarities that the jam chain has to a sort of smart contract chain. We call these encapsulations of state services. We don't call them contracts. There is a good reason for this. Creating a new service is permissionless. Anyone can do it. So this is a little bit like you can create a smart contract on a smart contract chain, right? It's unlike what you can do in general on a substrate chain, where you need to be whatever the chain's governance is to be able to add a new pallet, right? So you can add a new service into the jam chain without asking anybody for permission, without going through any governance mechanism. Services are, they can be defined as a sort of a tuple. If we're looking for like a formal definition, it's quite similar again to a smart contract. There's a bit of code there. There's a balance associated with a service as well. And there's some state associated with the service that's actually, again, fairly similar to what you'd expect on a smart contract chain. It's key value pair sort of thing. There's a couple of other bits associated as well that I'll go into. Code itself is split into 3 different bits, 3 different entry points. It's the same code blob, but it's got 3 different sort of ways of getting in there. And this is really the crux of what of Jam's model, what the service offering of Jam, what Jam actually wants to do. So the three sort of bits of code, the 3 entry points. It's 1 bit of code, sorry. 3 entry points into this bit of code are refine, accumulate, and on transfer. Okay. So refine is the bit that does the mostly stateless computation. Right? This is the bit that defines the transformation for the rollup for this specific service. Right? Accumulate is the thing that takes the output of that and folds it in to the overall state of the service. And then on transfer, as you might imagine, handles things coming from other services. Yep.
you're still mute.
Right. Sorry. I was just going to say that can we quickly draw parallels between what Gav has just explained here with kind of what we already have in the parachain lab. So one of the things that what it was saying at the start of this video was that like Gav was sort of speaking from this very, very abstract sort of lens of Polkadot, right? Like, and this is something that mathematicians do, is that they find a solution, but then their job is not done. Their job is now to abstract this solution and sort of make it applicable to a wider range of problems. And so Gav, he invented Polkadot, and then he's now going to say, okay, we're going to take this Polkadot and we're just going to make it super abstract so that it can now be applied to a wider class of computational problems, right? So, yeah, let's just quickly talk. What do you think about this idea of services, right? What from your perspective, what do you think that this is?
I don't have a lot. I think the services themselves is just just a terminology for like what we do on a core for a given time slot. And I think that bit of it is not changing so much. Or yeah, I guess that's like the definition of service. Let's cement that first. Like a service is like it's like some abstraction around utilizing cores. What I wanted to comment on, though, it's a little bit diverging from your original question, but is exactly what you said in that, like, this Polkadot 2.0 stuff is quite interesting in that it's not like, oh, we found a way to make it even faster. Oh, we found a way to make it, even more. It's truth is, it's actually like good in those regards. It's actually like, oh, we're going to make it more, we're going to change the abstraction. We're going to play with the abstraction levels. I think that's kind of interesting to know as well, or keep in mind. And I think in my mental model, it goes back to that original property that we talked about earlier, in that Polkadot is one of the few, or if not the only, that's doing like proper sharded execution. And now it's taking a step toward like providing that in this environment in a more abstract way. Should we talk about like what refine accumulate is in the current model? Like for a parachain service, what they look like? I think this is something that Gav will mention very soon, but we can already talk about it. Especially because you said you want to draw parallels between this and the existing system.
Yes, for sure. Let's do it. In fact, I actually wanted to also share some code of the validate block function, right? Like, because that is the current service, right? It's that Polkadot provides.
Kind of. I think it's the refine, in my opinion.
Okay.
It's the refine part. I think what we have now, like currently every parachain block is accompanied with some POV or some state that is necessary to execute it. And it's given to this validate block function. And actually wanted to touch on, in my opinion, I mean, everything I'm saying, by the way, is my best effort, so I might be wrong about all this. In my opinion, this is exactly what Gav is referring to as refine here. And this is, in fact, stateless in that the function validate block already receives the parachain block and the POV, the rest of POV, which is this partial Merkle tree of like information that's necessary. So it is actually kind of stateless. Does that make sense? Like the parachain validation function.
I wouldn't agree that it's stateless.
It's stateless from the point of, it's stateless as in it doesn't need the state of the relay chain. Like all of the state that it needs is already given to it as like a parameter.
But it does need the parent block, right? Because the relay chain stores the head of the latest head of the chain.
Yeah.
But
yeah, I mean that's part of the parameter stuff that I'm talking about. In that it's stateless, in that, for example, it doesn't like touch the relay chain state directly. It's, or most, I mean, let's put it this way. Most of the information that it needs is the parachain block and this parachain partial Merkle tree. That is all the data that is being touched in that block. And that is all given to it as an input. So it requires very little state otherwise. So to continue on drawing parallels, I think this is what we're referring to as refine here in this model. Refine happens on core, I think, in this model, as in not everyone re-executed, only a subset of validators re-executed. And then accumulate is the little bit that is right now, I think, somewhere randomly in the Polkadot code base. I don't really know where it would be. That the relay chain looks at this execution that happened, and if everything is fine, for example, updates the parachain state root on its own state. That's the accumulate part, which is very small. It's very simple, and that everyone has to do it. All the Polkadot nodes do it. Does that make sense?
Yeah, no, that makes a lot of sense. But I was actually going to say that I mean, the service is what provides the refine method, right? The service provides the refine, and I believe also accumulate as well. Actually, it provides all of these three things. So it's still correct to say that maybe currently the validate block is a service that provides the refine and accumulate methods.
Yeah, I don't know. I think, I mean, in the way that it's going to work out in the future is that not just one parachain will be one service. The entire parachain stuff is going to be one service. So like
a single service.
I'm actually not sure how that's gonna. Yeah, single service that will be all parachains.
Well, fair, but yeah, because you need to have multiple services. But I guess that means all parachains would share a single state.
So all the parachain related states will be but all the parachain related states is, again, for example, just the state root of parachains. It's not like literally the state of parachain, but the relay chain representation of all parachain states, which is probably some roots and I don't know, some block numbers at most, will be in one services state. Yeah.
Interesting. I mean, that fair. That makes sense. I mean, it doesn't make sense to have the same piece of code sort of duplicated on the relay chain.
Yeah.
No, that's fair. That's fair. All right, let's get back to it.
Yeah.
Okay. So we've got like an idea now. Our state is partitioned into services. You can add new services into the state, and the services have code attached to them. So far, so good. Very similar to how a smart contract thing works. What we haven't talked about is how the input to a service actually gets brought in. Well, we've talked about it a little bit, this refine and accumulate. I'm going to do too much. Work packages are effectively the input to a service. In fact, they're not specifically work packages, but a work item. Work packages can have many work items in them. Okay. Work package can have a few work items. Every work item is associated with a service, and it reflects the actual input to the service. This is where, if you're doing something like, I don't know, a parachain service, this is where you would put in the transactions, right? All that stuff to do with blockchain inputs. The refine entry point defines how we go from a work item, like an input, to a work result, which is basically the output of refine, right? And it's the thing that eventually gets fed into accumulate. So we have this two-stage processing. First refine, then accumulate. So work items are refined into work results, and therefore a work package, which contains many work items, is effectively refined into a work report, which is the results of the corresponding results of several items. Okay. A work package can be assigned. It uses one core for one time slot, always. One core on the jam machine for one time slot, 1 6-second period of time.
This was quite important for me. Can we pause here?
Now, how does it differ from a smart?
Because we also then move on. I think this is something when I was listening to this, I was trying to build a model of, and I think the answer was given here. like if you imagine like, you know, this jam as as like a 4-core computer, like there's 4 cores, like, so maybe like 40 validators, whatever, the CPU with 4 cores. At every 6 seconds, each core receives one of these work packages. So that's like the volume of information that's going. I wish to have the time to actually like build some visualizations around this. So you can imagine like a box that's like the CPU with 4 entry points that are the 4 cores, and there's like multiple columns of 4 work packages stacked up, or this is what is being provided. Every 6 seconds, every core ingests one work package. Yeah, and then, I mean, something that is touched upon maybe a little bit later is that, as mentioned, a work package is multiple work items. And each work item then associates to one service. So for example, the work that happens in one of the cores, in one of these 6-second slots, can touch on 3 services, be relevant to 3 services. Or the opposite, like maybe like 3 of the cores ingest 3 work packages and all 3 of them go into one service. For example, all 3 of them can go into the parachain service. Was that a reasonable explanation? Because this is something I want to, you know, I'm validating my own understanding.
Smart
here,
contract chain. Well, it's transaction.
You're still muted, Sean.
Yeah. I think it makes a lot of sense. I think that sure, like it doesn't make sense that a service can only handle one work package at a time, especially if it's the case that all parachains are going to have to use one service.
Yes. I mean, there's still, I mean, now I found like a question in what I said, in that there's like some kind of a race here, I guess. Like imagine, so you have these 4 cores and each of them ingest a work package in one time slot, 6-second time slot. And all of them are related to the parachain service. I don't know how the ordering of that happens. Well, I don't know if anything, the model I'm describing is correct. That's disclaimer. But even if it is correct, I'm a little bit unsure how the ordering then works. You know, like we first, because at some point this needs to be serialized, right? Like if a lot of cores are going to work with one service, at some point, and there's like parallelization here, like the work on different cores, the refined stuff is stateless, therefore it can happen in parallel. But when we accumulate, there's like some ordering that needs to happen.
Fair.
And I mean, not that it's not impossible, not that it's not possible. I think there needs to be some assumptions there on how these things get become sequential.
I mean, I don't think he's given us any clue to that yet, so we can probably proceed and see if that happens. Yeah. But I also want to quickly kind of talk about this slide, right? Like, I think that this slide is very, very important because it breaks down the core of the jam chain, but at the same time, it's the abstraction of Polkadot itself. In that, you know, like we already discussed, Polkadot provides guarantees. You know, it attests to the work that's done by its rollups, and then there are these assurances about the availability of parachain blocks. You know, we have that data availability protocol built before I think any other team in the space, and then there is disputes, you know, judgments if validators incorrectly attest to what is the state of a parachain. I think pre-images is a new thing, and also makes it a lot of sense in that you don't want to have to include a lot of data in your work package if it's the case that the jam chain already has this data, right? And so you can look up data that the jam chain already has. And then I guess finally tickets, which I guess he's referring to sassafras and this new paradigm of, you know, secret leader block election, block production leader election. And that's all. That's all the jam chain provides, really. Like, it's literally all it gives you.
I guess if you strip out all application logic from any proof of stake based blockchain and leave the whatever is rest, then these are the only transactions or extrinsics that you need to handle the rest, like the consensus and the data availability and such. And I think you're right in that the only somewhat feature that is beyond that here, and it's a little bit of a, yeah, it's a feature, is this pre-image service. I think that's something that we just, I'm guessing, you know, we added it for like frame and runtimes, and it was something that Gav wanted to take to Jam as well, and generalize it. But I think the other four, other than pre-image, are really like the bare bone things that a blockchain has.
Yeah, fundamentally. All right, let's get back.
Yep.
Transactionless. This is actually how Jam differs from, as far as I know, every other blockchain. There are no transactions in Jam. Everything that is all permissionless input first goes through a refine stage. So the service pre-refines all of the input, and then the input, that input is transformed into these work reports, these sets of work results. And then those work results make their way actually onto the chain. So there's no transactions, very important. So if there are no transactions, how does anything make its way from the external world in? Well, there's still extrinsic information, but these are not arbitrary, they're not of an arbitrary format. They are of a specific format. In most cases, there can only be one thing that the block author can put in its place. Now, there are 5 kinds of extrinsic in Jam: guarantees, assurances, judgments, pre-images, and tickets. Okay. I won't go too deeply into what each of these things mean at this stage. Guarantees and assurances are essentially the validators each getting together or putting forward their attestations of that a work result that help ensure a work result is indeed the correct result of its work item when transformed through the service's refine function. This is part of the security apparatus of the Jam chain, essentially. Judgments, again, are part of the security apparatus of the Jam chain, but they get used in exceptional circumstances, essentially when a work result has made it all the way through, and sort of, even though it's kind of broken, even though it's not reflective of the work items that it purports to be, has already been made its way through the system and has been since accumulated into its services state. At this point, we have to roll things back and we have to record the fact that this was invalid. Now, the way that we judgments generally come, in fact, I think it's a necessity that judgments come within 1 hour after, or at most 1 hour after the work report has been submitted to the chain. So basically, you've got this like 1 hour period where things could be not quite reverted, because finality will, in this case, pause until the judgment has been allowed to actually happen. In general, though, this is like a massively upper bound, and most 99.999% of the time, any possible judgment would have been done within maybe 3 or 4 blocks after the work package, and finality would only be paused for that.
You know, so just one more thing again, drawing parallels, is that it's already the case that Polkadot, Grandpa protocol already finalizes within 3 to 4 blocks, and like we discussed earlier, that's already predicated on the fact that the relay chain has come to sufficient guarantees about the validity of parachain blocks, and Gav just places an upper bound of over an hour, or thereabouts, on how long finality is allowed to stall for.
Exactly. I had some doubts about this as well, and this is one of the points that I wrote it as like a question to verify later, because I think it could be, I think if heard without context, it can actually be somewhat misinterpreted as it's also it's similar to the optimistic thing. People I think maybe draw a parallel to that like 7-day challenge period stuff, which is actually absolutely not the case. And because of this pessimistic versus optimistic system that we talked about, in that because Polkadot kind of forces its validators to like, hey, no, verify, like attest that this was correct. In most cases, as you said, within 3, 4, 5 blocks, all the rollups are checked by enough validators, and we can then progress finality. But this 1 hour is like an upper bound on how long this can delay in case there is a dispute or something.
Exactly.
That's my understanding.
Yeah, mine too. We can proceed.
That long. Okay, so those first 3 things actually represent the security apparatus. Pre-images are a service, a piece of functionality that the Jam chain provides specifically for the refine function. So I mentioned the refine function is essentially stateless. It is essentially stateless, but there's one particular thing that it can do that is kind of stateful, and that is it's allowed to look up the pre-image of a hash. So if it knows that there's a hash, and it knows that the hash, or it believes that the hash has been has its pre-image registered on the Jam chain, then it's allowed to ask for it, even though it's not necessarily known that the whoever it is that's actually executing this work package is synced to the Jam chain. I mean, this is a relative thing. Different nodes can be synced at different amounts. But there is logic actually on the Jam chain that ensures that this is secure. And for those pre-images to actually get onto the Jam chain, there has to be some way, right? And that's what this this type of extrinsic is for. This is actually of all of the things, this is the one that is opinionated. A block author of the Jam chain may choose to bring in one pre-image rather than another pre-image. There's nothing that like holds them to any particular pre-image. Whereas for those guarantees, assurances, judgments, and tickets, there are particular pieces of information, pieces of data, which the author either has or doesn't have. And if they have it, regardless of whether they have it or not, their only option is to either provide it or not provide it. There are no, they can't like provide something else in its place. Tickets are essentially anonymous entries into the block production mechanism. They do not immediately need to be provided to produce a block, but rather we run 2 epochs in front. This is part of an algorithm called Safrol, which is a small refinement of an original algorithm called Sassafras, which you may already have heard of. It's slowly being integrated into the Substrate SDK. I won't go too much into that. It's not so relevant for this specific talk. Now, one of the things that Jam aims to...
Actually, I want to touch a bit on Sassafras because I think it's such a very cool piece of consensus technology, right? And also because it uses snarks, and I've been recently very snark nerd sniped. So basically, Sassafras is an alternative to Babe, where Babe, as a block production mechanism, it's possible to know who are the block authors ahead of time. And the reason actually I know this is because I implemented this in Substrate. There's this RPC that you can call, and it will tell you all of the validators and kind of what slots that they've been assigned. And you know this from the beginning of the epoch, because it's the epoch header hash that seeds the assignments for all the validators, right? And so I guess the problem here is that if you know the public keys of the validators ahead of time, and you know their slots, you could also kind of discern who they are on the network, right? You can tell that, I'm seeing blocks coming from this node, always with this public key first before I see from anyone else. So I guess I can assume that this node is, in fact, this validator. And now also because I know what slots they're supposed to produce a block for, then I could actually target them at every time it's supposed to be their turn, I can just overwhelm them probably with a lot of invalid blocks, so that they miss their slot, they miss the slot to produce a block. And then I can then do this in turn, actually, for every validator and successfully stall the chain. But with snarks, we can then have this sort of scenario where instead of validators being required to of course reveal their public key alongside their signature, because that's how signatures work. You have to kind of reveal what is the public key of the person that signed the signature. Otherwise, the signature is kind of useless without this, right? We don't know what we're verifying against. You have to reveal the identity of the person. With ring signatures and snarks, because it's also kind of a snark underneath, is that you can have a commitment to all of the validator public keys, right? You have a single commitment, and then any of the validators can give you a signature, this ring signature, and you now no longer know who exactly they are. Actually, you no longer know who exactly they are, but you're still able to verify that this ring signature correlates to someone who is in that commitment of public keys, right? So now on the network, validators are essentially anonymous, because now you're receiving these signatures, and of course the commitment to all of the validators is on chain, but you don't know who is who, and more importantly, you no longer know what their assigned slots are, right? And I think that that's really cool, because Polkadot has always been about pushing forward truly decentralized technology and unstoppable technology, and this it might not make sense, it might not mean something to a lot of people, but it means something to the cypherpunks who care about all the possible, they're paranoid about all the possible ways in which a network can be attacked.
Yeah, that was I didn't know most of these details, but that was a very well explained description of what sassafras is enabling.
Yeah, no, it's
maybe
exciting.
I can just paraphrase it from my very let's say monkey brain perspective, like a layman's perspective. Previously, what they did is that validators publish a block and a public key, so you can then verify any signature in that block. Now, at the beginning of Epoch, there's this one rings, like a collective public key that is published, and later on, that can be used to just verify that any signature corresponded to someone in this committee, but you don't know which one.
Yeah, fundamentally, and this sort of was the reason for this new direction in block production algorithms or leader election algorithms. All right, let's get back to it.
Yeah, I was wondering about something like the pre-image service, where Gav said like the nodes are not guaranteed to have like a particular pre-image, like that. No one is holding them to having a particular pre-image. So how do you think that is going to work? Like, let's say work item requires this particular piece of code to run, but this node does not have that, or the node that work item is submitted to doesn't have that pre-image and just provides something else. I'm trying to like figure out how that's going to work for like when it's generalized or something.
Yeah, don't know, or not sure.
Yeah, I mean, neither am I, honestly, but
I guess we can just person you're submitting to has the pre-image in it, yeah. Maybe you can like batch it with the work package.
Like, one thought I can just put out there, and maybe it helps, is that I think one way to achieve it is that any pre-image that could be requested and is propagated with this extrinsic is then on the jam chain's state. And if that's the case, I think then that means everyone has it. Although maybe that's not the case, because again, I saw Gav has a few sentences here that also I didn't quite get, in that, yeah, someone might not have it, but we guarantee everyone will. I don't know what that exactly refers to, but maybe I can draw a parallel here to like what we could implement today on the existing Polkadot 1.0. This is actually one of the, I would say, among the coolest features that for just sake of priority or like for prioritization reasons never got to be implemented. But you can already imagine on the Polkadot relay chain, for example, all parachain or a parachain can go to the relay chain and submit a lot of information once to the relay chain, as some blob and as some data, and also pay some deposit for it. And now this data that belongs to a particular parachain will exist on the relay chain state. It's just stored there and duplicated, and everyone has access to it. And from this point onward, that parachain's blocks, instead of needing to repetitively put that on the POV, can actually say, go read it from your own state. You probably have access to it. So I think the use case here that would have been useful was that for a lot of smart contract chains, for example, they could have a logic where they say they already submit their top 10,000 contract codes as a pre-image to the relay chain, and then they don't need to or include it in the POV anymore. So I'm pretty sure what is being conveyed here is the same feature, but now on the Jam model.
Yeah, I really like that now this functionality is being enshrined, because I was talking to, I think it's Andrew who's working on this contract stuff. And I remember I was asking him that, because they were looking into, okay, how can we make the POV more efficient for smart contract chains? Because like you said, you have to include everything, including the code for smart contracts into the POV. And that's not necessarily, like efficient to do this. And they were like, okay, we're going to Merkleize the code, or okay, we're going to like make it more smaller and all of this stuff. And it's like, and I just asked him, what's stopping us from just putting all this code on the relay chain and just having the relay chain just give it to us whenever we need it? Of course, we have to think about state rent, which is maybe not something that a lot of people want to have to think about. But I think state rent is necessary, right? Like we can't escape it, otherwise we have state bloat. And this is something that Ethereum has today, is this unlimited state growth. And of course, it's because there's no incentives for anyone to delete anything from the chain. Right? It's like, I just keep stuff there, and you just keep it for me for free, and that kind of burdens thousands of other people on the network for no extra reason. Doesn't really make any sense, right? So state rent is going to be necessary, in my opinion, for any scalable smart contract platform, right? Because once a smart contract is no longer in use, you should go back and delete it, right? Like you should say, well, we're no longer using this thing. Let's destroy it. Let's get back our money. Otherwise, like I said, this just becomes a problem for everyone else.
Bring is a reduction in the opinionation. Polkadot's quite heavily designed around one particular service profile, right? The delivery of parachains. This is what the original Polkadot paper had in it. It's like, parachains. Polkadot is a service for parachains. In delivering that service, Polkadot created a number of very useful subcomponents, one of which was the distributed data availability system. Another one, which was the essentially an optimistic roll-up system with very good and proven security guarantees. And it's essentially, Jam could be considered essentially a reduction in the level of opinionation. Basically, a greater level of abstraction and generalization, so that it's easier to use these underlying components in a way that you would like to use them. And there are some use cases which it's very hard to use them for. And this is alleviated with Jam. And I'll go into that in a little while. All right.
I think one thing that we may have skipped is the nature of the transactionlessness of the Jam chain. And from what I understand, Gav is saying that transactions will not be gossiped. Instead, they will be inserted into the block by the block author. I guess, which also means that pre-image lookups are asynchronous, right? Because a service will request a pre-image in one block, as part of maybe it's refine, or sorry, maybe it's accumulate. And then in another block, another validator will provide the pre-image for that lookup.
Maybe, yeah. I'm not sure. I'm not sure if I fully know what is meant by transactionlessness. I think it might be that it's end user transactionlessness. You know, as in like validators still, of course, put some data. Maybe you can, to draw a parallel, maybe it's a chain that only has inheritance. Maybe that's a
Yeah,
good way to put it.
fundamentally, yeah.
But there should still be ways for, or I'm guessing like if a validator, for example, wants to put an inheritance, wants to put make a pre-image available, probably it will propagate it to everyone. Yeah, I'm not sure. But to draw another parallel here, I think that's something we can continuously doing as we're saying here. Jam is from like Gav and Polkadot has continuously talked about this end goal where the relay chain is free of transactions, end users. Like DOT lives on Asset Hub, staking lives on a staking chain, governance lives on a governance chain, and the relay chain is really just doing nothing. Jam is like that from day zero, as in end user stuff is on services from day zero. There's no end user functionality on the Jam chain.
Yeah, exactly. My thoughts exactly as well. And so in this world, like, you know, validators cannot be signing transactions, right? Like, because they're the only ones on the network. So they will be sort of inserting them as an inherent into their own blocks.
Yeah, I think this comes up later in this talk that there's even no transaction queue, and you can do more clever transaction propagation mechanisms again because there's no end user transactions.
Right. Yeah. Let's get back.
All right. So, as I mentioned before, Jam is permissionless. So Jam hosts code very similar to a smart contract chain in this regard. People can upload code. They can expect Jam to execute that code. It also hosts data, this lookup, this pre-image lookup that I just talked about, and state, essentially very similar to a key value pair, key value store. Anyone can introduce new services. In fact, the first service that would be in the Jam Genesis block would be a service that enables people to add new services, right? Since Jam itself doesn't have any way of transacting, of accepting transactions, there's no immediate way for anyone to create a service on Jam. So there has to be a service that starts in Jam to allow people to, you know, go through it and create their own services. So that first service will indeed do that. Services are not limited. They don't have any particular limits on how much code, data, or state they can host. It's all crypto economic based. So the more, essentially, the more DOT your services has, the more DOT your services have deposited with them, the more data, the more state they can have in them. One example service, just to put something in your mind. What is a service? Well, you know, it's a pretty abstract thing. What is a smart contract? It's a pretty abstract thing. Well, what is a service? An example service would be the parachains service, right? Not a specific parachain service, but the parachains service. Essentially, all of the Polkadot 1.1 functionality would be contained within a single service on Jam, right? But the kind of cool thing is that other services can be added that provide other functionality, but still use essentially Polkadot's distributed availability system and essentially auditing and guarantees system for computation. All right, let's have a deeper look into the service model. So when you make a service, this is the model that you have to express what you want to do under. I mentioned before, it's a two-stage thing, refine, accumulate. In fact, there's this third entry point on transfer. Refine accepts potentially up to a lot of data, 5 megabytes of data. Okay, so really substantial amount of data. This is roundabout. This 5 meg figure is, you know, potentially it could change obviously by the time of launch of deployment, but it might be that if we can manage 6 megs of data, that would be quite nice, because it would be every time slot, and a time slot is 6 seconds, so it would be a very nice round 1 megabyte of data per second. Refine yields up to 4 kilobytes of data, right? So you've got this like big sort of compaction factor going on. Why? Well, because this is the nature of the distributed availability system, right? It's distributed. You can't have all of this data making its way into this single sort of crucible that is the accumulate function, that is the on-chain logic. So it's important that we compact somehow. We provide an expression of this 5 megabytes of data, whatever that means, in terms of the changes to the overall state of the system. It's important that we express that in this 4 kilobytes. So to give an example, for a parachain, the 5 megabytes of data would be something like the proof of validity block, right? It's basically this bunch of information that includes the block header, the transactions, and any witness data that the block is going to draw upon from the parachain state. The 4 kilobytes of data would be something like the state root after all of that has been integrated into the parachain state, as well as maybe the message queue heads, so you know what messages have been sent from the parachain, and maybe some header data, some header information for the most recent header of the parachain. Essentially, it's the stuff, if you're familiar with the internals of Polkadot 1, it's the stuff that will go into the candidate receipt. The refine function can execute for up to 6 seconds of PVM gas. Now I'm going to go into what the PVM is in another slide. Essentially, it can execute for the full block period, right? At the moment, PVFs can execute, I think the limit is 2 seconds, so it's about a third of the period. This can be because PVM has basically secure metering, and because there's a few other optimizations that we're doing, we can actually extend that, so we can process 3 times as much stuff. The refine function also gets some contextual information on what it is on the world around it, that the work that it's doing is being produced in. In particular, it gets information on what other things are being refined at the same time. Why is this important? Well, it means that you can construct work packages that have multiple services, work items of multiple services in them, which are codependent. And this then enables certain things like, for example, accords, and the ability to have one service, like, I don't know, make that like some sort of EVM service, interact synchronously with a parachain. Inside of Refine, you can also make pre-image lookups. So this is the thing that I mentioned before. If you have a hash and you believe that the pre-image is available for that hash on the jam chain, actually on the chain, then you can request the pre-image by giving it the hash. What this allows us to do is, for example, look up code. So we might have, for example, a parachain code where you don't want to supply a parachain code, which could be, I don't know, upwards of a megabyte. You don't want to supply that inside of the work package. That would be a waste of the 5 megs, right? Every time you want to run the parachain supplying the same 1 megabyte. So instead, you store the 1 megabyte of code on the jam chain, and you just have its hash in the work package. You say, yeah, I would like the pre-image to this hash. This, for what it's worth, is what we already do on Polkadot 1, but we do it in a slightly suboptimal way, and very much not general. Now, that's refine. That's the first stage. That's the bit that does all the work. That's the workhorse, but it's largely stateless. Then we've got
So I wanted him to finish talking about refine, but there was a part that I'm actually very confused about, and I think we kind of already touched on this. Is that he says that you can have work packages that are interdependent, and in refine you kind of have contextual information about other things that are being refined at the moment. But then we know that these things are actually happening in different cores, right? Like they're not happening in the same core as your refine is being executed, right?
Yeah. I think both. I think both are possible. And if anything, now I think I had a realization around that. So as long as, so work package is multiple work items, and every work item corresponds to one service. And every work package goes into a core. So you can have 3 items going into one core, referencing 3 different services. And these 3 services can have interdependence. And I think the killer feature that's being enabled here is sort of like synchronous composability, as in like they can easily, it's, you know, within everything that goes into one core can synchronously talk to one another. But I think once 2 work items belong to 2 work packages that go into 2 different cores, I don't think you can have this synchronous composability anymore. And that's a model that I've also have in the current Polkadot system. Again, this is a feature that is not implemented yet, although it also wasn't possible because this agile core time stuff was not around. But now that agile core time is around, in its full form, you can have one core in one block processing 4 different parachain mini blocks, and these 4 can actually now talk to each other synchronously. There's no need for that sort of, I mean, they can still use XEM, but it's kind of like redundant, as in like, then they can actually talk to each other synchronously. So in principle, again, like things that are being mentioned here, it's good to draw a parallel and also emphasize that they are principally possible in Polkadot 1, but you know, Polkadot 2 is already making this, like before even implementing them on Polkadot 1, is implementing them in this general way.
That makes a lot of sense. So if they're all in a single
One
core,
of you should mute, yeah.
So if they're all in a single core, then yeah, I guess they can synchronously compose, right? Like I run one parachain, it passes some output to the next parachain, and then you know you might even call back the calling parachain, right? Like to pass back the results. I wonder if there will be like an async await API that kind of abstracts this in a very clean interface, so that developers are not having to do callbacks and you know just descend into callback hell. I think that might be interesting.
Yeah. But I think a good thing to keep in mind here is, I think one of the understated facts about the ecosystem and XCM is that if you go to the XCM format, one of the first principles is that there's like 4 A's, right? And the first one is that it's asynchronous. Like people always say XCM is complicated, but truth is it's designed for asynchronous environment. So it was designed with this original model of like, you have, I don't know, 20 cores. Each of them is running one parachain in this long running format. So, and then these parachains want to talk to each other. And this communication, because it's from one core to the other core, is always asynchronous, or will always be asynchronous as far as I know. But again, with Agile Core Time or now with Jam, we're going into the realm where we can have like a couple of things, be it parachains or work items, running, sharing one core for one time slot, and everything that is within that is synchronous. And therefore, I mean, again, you can still, for example, use a language like XCM there, but it would be probably hugely redundant.
Yeah. I mean, I'm even looking at sort of the control flow of this sort of synchronous composition, like inside of the code, right? Like I want to say call the Hydra DX parachain and have it swap some items and let me know when that swap is completed, right? So
if it's within a core, there's no let me know, right? It's like a function call that returns immediately. But I guess the programming interface could be, right? Like if it's synchronous, it's like if it's within the same core, it's you go to the other and you come back, and then in principle at least.
Yes.
If you want to make it more, I think this is part of like this other idea that is discussed even less, core play, that is something that Gav eventually wants to build on top of Corejam, is in core play, there's this idea that you abstract this away with Rust's async await model. So in your code, you just say, please go to the Hydra, like we're in the parachain service. I am, I don't know, parachain Akala. And I want to say, please go to the other parachain Hydra and call this function for me, dot await. And if in the work package where I'm being processed, Akala is being processed, Hydra is also being processed, this await is instantaneously returned because you're in the same core, it's right there. Whereas if you're in different cores or maybe even processed later, then that will pause and resume later. And then you could have then you can have execute a little bit in one 6-second block, but because they hit an await that cannot be fulfilled, they will be paused, and who knows, 5 blocks later, because that await has been fulfilled, they will resume and continue. This is core play, by the way. This is I think a bit next level, and yeah.
Oh no, I really. Yeah. I was gonna say that actually this is something that I've been thinking about for the longest time. You know, is the control flow for asynchronous like communication between blockchains. Like it sucks fundamentally because you now have to expose sort of call back. Okay, once the results return, call back this function, especially because we're building Hyperbridge and in the APIs that we provide, like okay, you can send out a request. But in order to receive the response, you can't do an await, right? Like it would be cool to just do an await so that it's kind of, in that context of code. But now you have to have this, aggregated context for all the possible responses that you can receive in a different piece of code. And that just sucks fundamentally. Like it's not great. So this would be amazing, actually. This would be amazing for cross-chain communication.
Yeah, and I think like the results of the refine, because it can be anything. So I don't think it's like fixed to be something particular. So it can just be like a snapshot of the previous execution, then that'll be persisted, and maybe when the result comes back in another work package, you can continue like the execution or something.
Yeah.
All right, let's get back.
Got accumulate. What accumulate's job is to do is to integrate the output of this workhorse of refine actually into the world state, into this global shared singleton, right? Into the blockchain. Now, accumulate accepts multiple outputs from refine, all of the same service, right? Don't forget, refine and accumulate are both entry points from a code blob that is specific to a service. It accepts multiple refine outputs, basically a big vec or slice, whatever, right? And it processes them. And it can do what it wants as it processes them. And it can execute for a much smaller period of time, per output around at most 10 milliseconds. And this depends whether the work package it has many different work items in, or if it's just one. If it's just one, it gets the full 10 milliseconds per work output. If it's many, then that's shared between each of the outputs of the work package. Crucially, and in big difference to refine, it's stateful. This means it can access the state of the jam chain. It can read the storage from any service, and it can write to its own key value store. It can also transfer funds and send a little memo when it does transfer funds. And it can also create new services, obviously, upgrade its code, request the availability of a pre-image, and a few other bits that I'm not talking about. Incidentally, and I actually forgot to mention this in the refine model, both of these can invoke child instances of the PVM. Yeah. So you can make a new instance of a PVM that's sort of sub-instance a virtual machine, and you can put some code in there and put some data in there, set the memory to whatever you want, set the stack even to whatever you want, and then kick it off and let it run for some period of gas, and then it will come back when it's done. So it's a...
So actually, I wanted to quickly talk about this because I kind of have a small understanding of Polkadot, today, and I understand that in Polkadot there is an on-chain WASM interpreter, right? Like the WASMI, which is then used to execute parachain blocks, which are in WASM, right? That's I believe kind of the current model. And the reason for that, and the reason that code is not in the client, is that I guess WASM is indeterministic, right? So you can kind of have consensus faults if it's not on chain. Is that correct?
I mean, the code is on chain, but I think in technical levels is actually where parachain stuff is using compiled WASM. So clients actually compile the WASM once, and then they can execute it much faster, and it's just generally way more efficient. And I don't think actually there's anything undeterministic about executing WASM. If anything, it must be, I'm not an expert, but it must be one of its properties for which it was chosen for Polkadot, or generally consensus critical operations, and that the same WASM code or bytecode would execute the same regardless if it's being interpreted or compiled or executed by what compiler and interpreter and on which platform. So it should actually be pretty deterministic, or 100% deterministic.
So, but Gav is now saying here that I guess rather than I guess having or needing to run an or sort of an interpreted version of the PVM, you can actually invoke the jam chain's own PVM with some code and get the results for that execution.
Yeah. I think what this is being referred here is like the ability for like the main, like for any service. So any service that's being executed in its refine, I think was mentioned. The refine is expressed as some bytecode that I think hasn't been really expressed here explicitly, but it's in this PVM format, which for the sake of simplicity, you can say it's in RISC-V bytecode. What it can do is provide some bytecode and actually ask the jam chain to execute. It's kind of like spawning a child process, which for what it's worth, we allow this actually in Substrate and Frame as well, but it's just like, it's not used to its full extent because of some limitations. And I think there's also something with WebAssembly being really shitting for that. Something with, I think it's mentioned later, like the stack being something that I forgot, I don't know.
Yeah, I think it says the stack is off machine or something.
Right. Yeah.
Very, very flexible model for computation. Onwards to on-transfer. So on-transfer is also stateful. You can alter its alter the service's state. It can't do any of the higher level stuff like, transferring funds again and upgrading code and so forth. That's specifically for accumulate. But it can look at other services' state and alter its own state. And this really is there so that you can allow for services to communicate with other services in a albeit asynchronous fashion. So it's a little different from many smart contract platforms in that this interaction of the encapsulated components, smart contracts or services in our case, this interaction happens in an asynchronous fashion. You fire off a message along with maybe some tokens, and then on the other side, at some point later, actually later in the same 6-second execution period, but still at some point later, the other service will get it and can execute upon it. There's no return path. If you want a return path, you have to do a transfer back, basically, or possibly change your state in some way that the sending service is going to can expect it and look at it later. Both accumulate and on transfer are written so that they can be executed in parallel. So the different services accumulates and transfers can all execute at the same time. This allows for, it's not really exploited at the current design, but it would allow for future designs to actually have more than this 10 milliseconds of gas. In principle, there could, for example, be a secondary core, CPU core, utilized for executing certain accumulates.
So Ken, I guess you got to leave soon, but any things you want to share with us?
No, thanks for pausing and giving the opportunity to sort of like gracefully leave rather than needing to do it abruptly. Yeah, I think this is a great time to like have such sort of like collaborative watchings and, you know, go into the depth of these topics. So I'll make sure to watch the rest of this later. I'm also hoping to write like my own interpretation of this in the coming week or so in a short block format. So I hope that also helps the rest of the community. But yeah, continue, and I hope you enjoy the rest of this jam, I guess.
Yeah, for sure.
Bye.
Bye. All right, so and then there were two. We keep it going. Nothing stops this trade.
And giving them much greater amounts of gas to use. All right, so let's move on. PVM based, PokerVM, or it's sort of actually it's morphed a little bit. So for those of you who read the forums, you may already have heard of the PokerVM. It's a parity guy, Jan, has implemented a RISC-V transpiler, basically, with some modifications that make it go really very, very fast indeed. The spec of the machine, so the sort of design, the ISA, if you like, is de facto PVM. The actual implementation, Jan's implementation, will stay with PokerVM. So it's PVM based. So the design of the protocol, PVM based. Not to say no one else, you know, obviously other implementations of PVM are not only possible, but encouraged. It's the PVM design is based on the RISC-V ISA. Don't know if you're aware of this. RISC-V. It's like, you know, it's been around for almost 10 years now. It's a very simple instruction format. I think at its basic, at its core, I think there's only, I don't know, 20 or 30 odd instructions, and they're mostly very simple things like, you know, and or add. PVM adds a few extra instructions. The nice thing about the RISC-V ISA, other than that it's very easy to transpile into common hardware formats like x86, x64, and ARM, is that it's well supported by tooling. So LLVM, I think it actually just recently got merged. The RISC-V output platform, whatever, is actually part of the LLVM official targets now. Now PVM itself is very simple. It should be possible to actually implement a compliant PVM, admittedly interpreter, in you know, a matter of a few days, rather than something like WebAssembly, which would take probably quite a lot longer. It's secure, by which we mean it's sandboxable. It's got various guarantees over execution, and it's metered, or at least it's friendly towards being metered. And of course, deterministic, consensus sensitive, capable of being used in the sorts of applications that we need. It can host arbitrary code. What do I mean by arbitrary code, and why is it different to WASM? It's a pretty basic machine, right? If you've studied computer science and you've sort of been introduced to the sort of, a very, very simple machine, it's not far off that. It doesn't have much of the complexity that you might otherwise find, nor does it have much of the opinionation that you might otherwise find, or optimizations for certain use cases. WASM is ultimately optimized for a web use case, and this is sort of fine in most circumstances, but one way that it's not so fine is how it handles the stack. The stack is not handled as part of the machine itself, but rather it's sort of off machine. And this creates certain issues when you want to use it for things like continuations. Now, continuations can be really very helpful thing to have, particularly when you're doing stuff like asynchronous programming, and that's probably something that some of you have come across if you've tried to do any XCM. RISC-V being such a simple and sort of regular machine just puts the stack in a bit of memory, which means if you snapshot the whole of memory, or at least the pages that are actually used in memory, you will end up being able to have continuations just by the by. It will happen naturally. There's nothing extra to do. And this is something that we very much intend to make use of in some of the use cases for Jam. Now, as it happens, PVM also achieves incredibly fast execution speeds when run on regular hardware. And as I say regular hardware, I mean basically x64, but also potentially ARM instruction set, something like the M1 or whatever. How fast is blazingly fast? I asked Jan for some updated benchmarks. He hasn't got back to me yet. But as of the most recent benchmarks, about the same speed as WebAssembly when it's the fastest WebAssembly transpiler when it's not metered. When WebAssembly transpiler is not metered. So we can do metering for free, basically. And we get all of this extra helpful stuff thrown in as well. The continuations in particular make this a potential game changer for when we want to write code that is meant to go, that is meant to scale across something multi-core, something highly parallelizable like Jam. And to be honest, this is how, realistically, this is how all blockchains are ultimately going to scale, right?
I wanted to make a comment on on the continuations. Of course, Gav gives some more context as to why Polkadot's moving away from a WASM-based architecture to this RISC-V architecture. Apart from the fact that it's fast, there's metering for free. Metering meaning we can, I guess, we can sort of count the number of instructions and place a hard bound on how many instructions do we want to execute. Of course, it makes benchmarking completely irrelevant. I hate benchmarking, by the way, and I'm sure all the other substrate devs do. But more importantly, I guess, is this idea that you can take a snapshot of the stack, right? You can just take a snapshot of the stack, and that's because the stack is actually a property of the VM, of the virtual machine. And you can imagine that a single core executes a service up until a point, stops executing this, it takes a snapshot of the stack, and then another core can resume and sort of continue that execution. So that's what Gav means by continuations, is that you can pause the execution on a core, have another core continue that execution, and then already this looks like, and for those of us who are Rust developers, this already looks like the Tokyo multi-core runtime, right? Like if you've looked into the futures execution model, Tokyo in particular uses something called work stealing, right? They call it the work stealing algorithm, and so what happens is each thread, in the beginning of the execution startup, is that each thread is kind of assigned a task. But because these tasks can pause at any time, they can halt while maybe they're blocked on reading from IO. Maybe that's maybe networking, maybe reading from a file, and they're kind of waiting for the kernel or the hardware itself to make those bits of data available. Is that they can then try to take something else from sort of what is the pending queue of tasks. So they're not idle, right? So the whole point of Tokyo's work stealing algorithm is that we want to utilize all of our cores to the max, right? So we don't want anyone to be idle. If you encounter a sort of pause or breaking execution, pull something else from the core, from the sort of pool of tasks, and return whatever it is that has paused, and then someone else will of course pull that task and then continue it, ideally once the data is not available, or they might try to continue it, the data might not be available, and instead of sort of idling, they will just drop it back and then try to pull something else off the sort of queue of tasks and try to execute this. And I just wanted to say that this is real scaling. Like we just saw, the Ethereum community release, data availability in EIP 4844, and they're trying to scale the availability of data for rollups to commit their blocks to. And whereas Polkadot is going in this completely multi-core dimension, where they're trying to scale the number of cores that on-chain logic has access to, and sort of can be run by. And as you can imagine, we can now scale computation greatly. I think this is a very, very important distinction to make. And that's why I made that tweet, that it seems that there are two paths in blockchain scaling. It's either you create this data availability, or rather you create this cryptoeconomic floppy disk. Because when you really think about the IO performance of using a distributed network as a data layer, you try to write to that data layer, you find out we basically have the same IO performance as what we did, when we had floppy disks, right? But now, if you look at Polkadot is going to match modern day computers in terms of computational throughput, and I think that's a very important point and a very important distinction to make, with Polkadot and other sort of scaling ideas.
Yeah, and I think in terms of semantics, the continuation of the PVM, it's where the await is going to come in, where a service awaits. We'll probably just take a snapshot of the stack of the PVM and accumulate, pass that to the accumulate. So maybe in another work package that wants to continue that execution, they just pull that snapshot from the state and continue executing when some data is available. So it's provide true async. I think this the true model for async, an async paradigm in blockchains generally.
So yeah, I agree. So and maybe to harp a little bit more on scaling, is that if you're a systems engineer and you build systems code that runs on bare metal hardware, is that okay? So you are running code on a single thread, and you realize, okay, I need to scale up the number of computation I'm doing on a thread. I can't be locked to a single thread. Immediately becomes clear that you need to sort of parallelize your work. You need to make it run concurrently, right? You need to have multiple bits of code running concurrently. You break it up into multiple processes, right? And they're all running concurrently. But now you have a problem. You fundamentally have a problem of state, of the program state. How do you manage a program state? Do you share it across all the cores, across all the threads? In which case you have to then use locking semantics, right? Because if you want to write to shared state, if two threads write to shared state at the same time, they will corrupt that state, and that will corrupt your program and basically force it to terminate. The OS, the operating system, will kill your program because it's trying to do something invalid. You get it, segmentation fault, core dumped. And so you have to do this in a very, very, I guess, in a way that the operating system will not kill your program, right? So you now have to have locking semantics where one thread will obtain the lock on the state, and then now other threads have to be stuck waiting for that lock to be available so that they can also write to that state. My point being that shared state doesn't scale, right? It's not very performant because now you have this idle threads that are kind of waiting, which is what we're just talking about the Tokyo model, is that you now have idle threads that are waiting for some data to be available, and that's kind of efficiency gains that are lost. And there's another model where instead of having shared state, you have channels, right? You have what we call consumer or multiple producer and single consumer channels, or multiple consumer channels, where instead state is sharded, essentially, right? State is sharded across all the different threads, and they just pass messages across, right? So they do some computation, they pass the result of that computation to whoever is interested in it, right? And whoever is interested in that state is holding what is the receiving end of a channel. And in that sort of way, you can have a single thread broadcast the results to all the other threads that are sort of waiting on some results. And at the same time, these other threads are kind of idle, right? They're probably doing something else, and then whenever some data is available, they can start to act on it, and it's entirely asynchronous, right? And so that sort of asynchronous model for highly efficient computation is what Gav has now taken from systems programming, all of the research that's been done on systems programming, and brought that into the blockchain space. And yeah, I think that's really that's just how you scale computation in general, right? Regardless of whether it's on chain or off chain, this is how you scale computation.
This idea of just like throwing faster and faster single core CPUs at it is not going to go very far, right? We already can see this in hardware. And if you've been in software for the last 20 or 30 years, you'll have seen this in the evolution of software platforms as well. Increasingly, there's a great need to think in terms of asynchronous, parallelized architectures, and the same will for sure be true in blockchain. So it's a consensus algorithm. Specifically, the block production algorithm is Safrole based. Now, Safrole itself, as I said before, it's basically a simplification of Sassafras. It throws out some of the less important bits that may still possibly be useful for parachains. So it's not necessarily that parachains are going to use Safrole. They may probably stick with Sassafras. But really, for Jam, one of our main considerations was to make this thing as simple as possible. Why? Partly because we want to ensure that it's as minimally opinionated as possible to maximize the potential future use cases. Another reason was to follow in the footsteps of Ethereum 1, yellow paper, and really try to get as many implementations of this thing as possible to try and kind of spread the expertise. Because at the moment, Polkadot is a very complicated little beast. It works, but good luck if you want to try and understand end to end exactly how it works. Well, with Jam, my sort of personal goal is to make this something that someone who is capable of reading and understanding the yellow paper would be able to read and understand within at least a week or so. So simplicity is crucial. So as I said, Safrole is a little bit more simple than Sassafras. For those who don't know, it's a snark-based consensus algorithm, a snark-based block production algorithm specifically. It uses snark specifically for their anonymity features, and it delivers constant time block production, almost entirely fork-free. There's a couple of instances where they're outside instances. They basically only happen when there's a net split or someone's being intentionally malicious. But there are a couple of instances where forks could possibly arise. But in all likelihood, unless there is something really crazy happening, Safrole will be fork-free. And the sort of great value for the anonymity is not specifically to keep validators' identities sort of a secret. In fact, when they actually produce a block, they give away their identity anyway, but rather for ensuring that the block production mechanism itself is secure, basically to avoid spamming. validators can't be DOSed.
So yeah, this is just basically what we talked about earlier on the stream, is that Sassafras basically makes block producers kind of anonymous on the network, and you can't tell when it's their time to produce a block, and so you can't really start to try to DDoS them and make them miss their block. So just quick context there.
Very crucial point, perhaps not so obvious. It's capable of offering the same service as Polkadot 1, right? As what is happening at the relay chain at the moment. Jam can host Polkadot 1 style parachains. That's designed with this in mind. The main sort of elements that would change on the substrate side, substrate and Polkadot SDK would still be used, but the PVF itself would be retargeted. So instead of targeting WebAssembly, it'd be targeted towards PVM. And we actually expect PVM, because it's such a minor alteration from RISC-V, and RISC-V is now a official LLVM target. We expect PVM to be an official LLVM target before this stuff is deployed. Now, it doesn't just host parachains. It does other stuff that Polkadot can't do. Oh, the relay chain, I should say, can't do. It brings key features to parachains. In particular, it brings the possibility for removing most of your benchmark work and alleviating that in the future. It brings the possibility of having this multi-instance, multi-sharded smart contracts to police and enforce certain rules of interaction between parachains, accords. And it would necessitate, I don't want to say deliver, but necessitate full XCMP, which basically means lifting that limit on on how much information can be passed via, passed between parachains, usually using XCM. Now, Jam is...
So I just want to talk a bit about some of the stuff that Gav just talked about, which is like, okay, we're removing benchmarks. This is something that I've brought to the table, to the fellowship table, that it's the case that, like, and this is, we'll give you a bit of context as to how Polkadot works, is that since Polkadot is re-executing all of the, what is the parachain block, of course, that's now becoming a service, and that execution is actually going to be called refine. It's the case that actually Polkadot already places a limit on how long it's going to execute parachain blocks, right? It's going to execute parachain blocks, and pre-async backing, this was around 0.5 seconds, right? So half a second. Before, of course, discarding it, because it would cause it to sort of lose sync. If you can imagine if it's processing blocks that are kind of have unbounded computation. This is, of course, not good for the validators of the relay chain. And so they actually cap how long they're going to execute your block for. And if your computation is sort of outside that boundary, they will drop your block. And so this made me question, okay, fine, then why is it the case that we need benchmarks, and why do we need to define what is the weight of a block? Because actually these things are not very easily definable. And I'll give you an example here. For instance, Hyperbridge, one of our products at Polkadot Labs, it's a blockchain that processes proofs, specifically Merkle Patricia proofs. It processes, even general everyday Merkle proofs. And the problem here is that it's not very easy to benchmark this sort of computation of proof verification, because it's the case that these proofs have variable size, right? They have variable size, and they, depending on how deeply or how shallow the tree is, they will have very different computational requirements, right? So this is very, very dynamic, and you actually cannot benchmark this. I don't think anyone can benchmark this. There's no way you can put sort of upper bound on what the computational requirement for verification of proof verification should be. So it was very, very clear that benchmarks were not really a good model for metering computation from the start, especially like I said, because the relay chain already meters block reduction in terms of seconds. And then I guess, of course, async backing, now with async backing, that limit has now been quadrupled. It's now 2 seconds. With the jam chain, it will now become 6 seconds. So that's a full, I guess that's like 12 times or 12x increase in computational throughput from pre-async backing. But it's really, really great to see that now benchmarks will no longer be needed, and we can just meter blocks per, I guess, instruction of the PVM that they execute. Accords, we already talked about this. Accords allow for parachains to opt in to some shared code, and that shared code they're not in control of, and so they can't change it. You can kind of see how it's an accord, like Gav describes here. Full XCMP. This is interesting, and I think this is one of the sort of pieces of the presentation that really caught my attention, is that Gav also recognizes that the current model with HRMP and passing messages through the relay chain doesn't scale. This is not a scalable solution for message passing, because essentially the relay chain forms a bottleneck between message passing. And you can imagine if all the parachains all at the same time wanted to pass messages through the relay chain, this would deadlock messaging fundamentally. And this is why we went ahead and we developed ISMP, which is our own messaging, in-house messaging protocol that we use in Hyperbridge. And ISMP is super general and currently has an implementation for EVM chains as well. So EVM chains can also communicate with the substrate parachains through ISMP, and it passes messages entirely off chain, right? The only thing that the connected chains need to know is what is the state root, or more colloquially, what is the root hash or the root commitment to all the messages that that have been sent to them. And then through this very cheap root hash that's passed on chain, they can receive the Merkle proofs, sort of the pre-image of that root off chain, and they can process this. And of course, this means that messages are no longer bottlenecked by how much data the relay chain can accept, but it's entirely bottlenecked by how much the parachains involved can accept. And of course, this, I said, is from the beginning when we wrote our grant application to the Web3 Foundation, and of course our Polkadot Treasury application. For those of you who've been following Polkadot Labs for the longest time now, these were our reasons, right? We said that currently parachain messaging is bottlenecked, and this is a solution that fixes that. And Gav himself is acknowledging this share here today. So just a quick context on that, but we can get back to it.
Built with Agile core time in mind, not much changes on the Agile core time front. I presume people here are familiar with Agile core time. Yeah, nodding of heads, good. So this whole NFT sales market thing for core time, that would remain essentially unchanged. The main thing that Jam adds to Agile core time is the ability to not simply target core time at a parachain, but to target at, well, essentially arbitrary sets of work packages. Yep. It has an entire layer that I don't have time to talk about, unfortunately, today. That will have to be the subject of a future talk. It has an entire layer that handles authorization. I say an entire layer. It's like 3 equations, but it's like it has an entire a small section of design specifically on this authorization system that enables very agile authorizations to go along with the Agile core time. Now, Jam's design is the hard bits. The great thing about sort of doing Jam is that the hard bits they're already done, right? The hard bits are things like distributed availability and managing the security for the computation, secure computation of PVM, of this input to output, these roll-ups basically. And that lets us concentrate on doing, the more easier, not always so easy, but some of the easier things. And certainly the things where if you get them a little bit wrong, it's not going to be super bad for the whole thing, for the whole system. Unlike, for example, if you get availability a little bit wrong and things just stop working totally. So one of the things that we've sort of been focusing on is optimizing networking. We optimized a few things. Networking for Jam uses the QUIC protocol. This allows us with very large numbers of validator. I mean, very large, not large like Ethereum, but still 1,000 plus validators. We can have direct connections between all of them. So when I say M to M, I just mean many to many. So essentially all 1,000 plus validators can have a persistent connection to each other without, potential issues with sockets and so forth. We avoid gossip. So gossip as much as we possibly can. There are some instances where, in very, very niche edge circumstances, there may still be some like random selection message passing stuff. But basically gossip is avoided, mostly because we don't need it, because we don't handle transactions. We handle transactions are removed from the protocol. We just handle these very fixed function extrinsics, and with the fixed function extrinsics, you kind of already know exactly who they're going to go to, and you know whether to keep them or not. So we don't really need this sort of optimistic gossip thing. Where we do need to distribute something that's not point to point or within a very small subset, we use grid diffusal. Which I think may already actually be implemented in Substrate, but in any case, this is not merely something that is additionally implemented. This is our primary mechanism for sending out information across the whole validator set. Grid diffusal, for those, if you can't already guess, basically we arrange the validators into a grid. And we send the package, by a row, and then each item on the row, each node on the row sends it to all members of its column. This provides,
I just wanted to quickly say that I think that that's a very, very interesting, advancement in blockchain networking. Because previously, and this is one of the biggest problems. And I can actually go into depth about this, is that in the blockchain network, nodes cannot make any assumptions about what pieces of data another node has. Give you an example of this, right? When you create a transaction and you broadcast that transaction to a node, that node, it can't make an assumption that, well, all these other nodes must have seen this transaction, right? It just sort of floods everybody that it's connected to with that transaction. When it gets to another node, of course, this node might say, well, I just received this transaction from node A, I'm node B, I should probably not send this to node B, but I will flood everyone else with that transaction. And now say there was a node C that was connected to both node A and node B. Now that node is going to receive that transaction twice. Now I want you to scale this up to, say 10 nodes, say 100 nodes, say 1,000 nodes. How many times do you think a node is receiving redundant data? Like, this is highly inefficient. And actually, because of this, nodes cannot make assumptions about what pieces of data that other nodes have on the network. This is actually why blocks have to be bounded in size, because blocks are going to make round trips around the network, probably multiple times, in fact, especially if you're using very, very naive, consensus protocols, or very, very naive gossip protocols. And so if this piece of data is going to round trip, the entire network multiple times, imagine if that piece of data was now super large, say like maybe 10 megabytes, say 20 megabytes, say 100 megabytes. This places immense pressure on sort of the networking requirements of running a node, that it just wouldn't make any sense to run a node anymore, right? So fixing gossiping, especially in terms of, say, consensus, right? Say, how often or how quickly can a piece of data be gossiped through the network, especially in this scenario where data is round tripping the network, especially in a scenario where it's the case that every single participant in the network has to see this data before we can come to consensus about this, right? Which means we have to keep that data very, very small so that they can quickly get to where, quickly diffuse the network. This bottlenecks consensus fundamentally gossiping information on any P2P network topology bottlenecks consensus, and if you really want super fast consensus, like what Gav is describing here, then it would make more sense that it's entirely point to point, right? I can make assumptions about who has what data, and I just send them the data that I think they don't have, and it just ends there. They're not like spamming everybody with all the data that I just sent them. And this is going to bring even faster finality and even faster network performance. So just bit of a note there.
A pretty optimal way of getting data across the entire network quickly. Yeah. One of the other ways that we've optimized is pipelining. Now, this is something that I'm a little surprised hasn't been done before. The header of blocks in state-based blockchains since Ethereum generally contains the posterior state root, right? Basically, it's a digest of what the state has become after doing all of the various computation that the block implies. Yep. Now, this means that you can't send a header out. So you can't, when you're making a block, you can't send the header out until you've done all of the computation that implies. Now, there's some bits of computation you probably do want to do before you send it out, because they may imply, or a failure, or that the result of that computation may imply that the block is not valid. But for any of the stuff that you need to do that can't fail, to the degree that that sits at the end of the block, that you don't need to do anything after it that can fail, well, you can send the block out in principle beforehand if you are not required to know what that posterior state is. So with Jam, we don't put the posterior state root in. Instead, we put the prior state root in. So the state roots that are featured in the header run one block behind instead of one block in front. And because of this, it means that we can do all of the cheap stuff, like probably about 5% of the block's weight, or the time to actually execute the block. We can do that computation and then send the block out immediately after that point, distribute it to the other validators, and then carry on doing the infallible stuff, 95% of the block's computation, effectively just the accumulation, ready so that we can check the next header that we get prior state root. This means we can effectively start constructing the next block before we've finished executing the last block. So we can publish one block, receive, start computing, and start building the next block, all before actually having executed all of the implied computation of the current block. This means we don't need to be quite so pushed for the computation that we do in this 6 seconds. So, for example, if we have 6 seconds between blocks, which Polkadot does at the moment, but it has to provide the posterior state root, then we can't use all 6 seconds for the computation, right? Because we have to do the computation, work out the posterior state root, finish up the block, send it off, have other people, the next block producer in particular, be able to import it, which means recomputing all of that implied computation, verifying the posterior state root, and then constructing the new block. So basically, we have at most half of that 6 seconds to actually do the computation. But by pipelining, we get up to the whole 6 seconds. Now, of course, you don't really want to use all 6 seconds to do your computation because, well, no one would ever be able to catch up normally to the head. They'd be constantly running behind. New blocks would be produced at approximately the same rate they could import old blocks. But what we can do is get much closer and probably get 3.5 seconds worth of block computation time rather than, say, 1.5 or 2 that we have at the moment. Now, one of the...
So I'll be the first to admit that I have no idea what Gav just said. Oh man, it's so what he's describing. He's saying, from the beginning, he's saying that look, we're not going to require. That's what he's saying. We're not going to require that block or validators execute the full block, the full relay chain block, which is interesting because this is actually supposed to be one of the fundamental jobs or roles of a block or a full node on the network, even as a validator of the network, is that you're required to check the full block. You're required to execute the full block, make assertions about what is contained in the block and what is contained in the headers. As an example, you're supposed to check that the transactions, when you kind of construct this Merkle root of transactions, they match what is the transactions or the extrinsic root in the headers. You're supposed to execute the block and check that the result of executing the block, giving the parent block that this, the state that this parent block or the state that this block points to as a parent block, gives you what is the post state root that is referenced in the header of this current block, right? So you're supposed to, of course, check that the number is monotonically increasing. There's a lot of assertions you have to do about a block. So I guess we still do all of this, but now we are not required to execute the full block. Now, I'm not really sure, I'll be very honest with you, I'm not really sure how this is happening, and I think this is something that we will have to maybe wait on more information when all of this is sort of standardized, because at this level, Gav is just sort of describing how the protocol will work, but he's not giving implementation specifics. But at the same time, he's saying that we will keep a state root, but it's just not going to be the post state root. It's going to be the pre-state root. So the state root value of state root in the header actually is the result of the previous block. So that means that we still get it somehow, and there's still some assertion in place that ensures that is valid, because we have to trust this, right? Like if this is not trusted, then actually we can never continue to build a trusted chain of blocks. So there's some mechanism in place that is actually going to verify that this pre-state is valid and correct somehow. But I think that's very interesting, and I'd love to see sort of more information about how this will work in principle.
Yeah, architectural differences with Jam over the relay.
I'm so like, without fully understanding how that works, like it's like a genius move, because you can see that most of the alternate L1s that claim like extreme speed today, they don't actually, they compromise verifiability for speed. Like they just send out headers without actually executing the block, and they achieve faster consensus. But now, since the jam chain is not going to be requiring the post state also, so you can achieve like fast consensus but still retain verifiability since the pre-state is there. So like if the validator sends out the header and the pre-state is invalid, then the other validator will start rejecting and disputing that header already. So that means he doesn't even need to like keep producing that block. They just dispute his the previous block that he like computed or something. So I think it's still like giving us these benefits of fast consensus while still maintaining verifiability. So I would still like to see how like the entire thing is going to work.
Relay chain is that the jam chain fixes quite a lot of the functionality, quite a lot of the pipeline. The relay chain does fix some things. I don't know if anyone can guess what. So it fixes the language, the meta language, really, by which the protocol is defined. It fixes WASM. Yeah? You can only upgrade a relay chain to another WASM blob. You can't upgrade it to like a PVM RISC-V blob or whatever. It fixes a couple of other things, or at least makes them very difficult to change. For example, the type of the type used for encoding the block header or the hashing scheme. So there are some things that that Polkadot does effectively fix, but Jam nonetheless fixes more things. It doesn't fix everything. In particular, much of the flexibility that we get from the WebAssembly meta protocol that we've used it for with Polkadot relay chain would still be similarly flexible with Jam due to its service model, right? Effectively, the service model takes over the upgradability responsibility, and the chain itself is not designed to be upgradable. Why not? Well, for 3 reasons. Firstly, simplicity. It's a lot simpler to not do that. Secondly, there has been a sort of a tendency towards introducing complex functionality and not removing old complex functionality from the relay chain because it can be upgraded so easily. Essentially, it just follows whatever the current state of the substrate SDK is. And there's no great need to simplify the substrate SDK. You know, we have Rust compilers and trait systems and stuff that kind of manages that complexity. But what it means is that essentially no one is going to be able to re-implement Polkadot, and that's unfortunate. The third thing is that it provides huge potential for optimization because we know what the various things that the Jam chain has to do are, and we know we can fix the parameters. We can optimize for those specific parameters. Things like network topology, timing can all be optimized, whereas they wouldn't be able to be optimized so easily when we have essentially the ability to alter everything with every upgrade. However, the application level functionality, things like core time sales, staking, governance, this can all be done, all be upgraded because it all sits inside of a service. Even stuff like the parachains logic, so the ability for parachains to service message queues and all this sort of stuff can be upgraded within the service. So Jam does one kind of application level thing. It's not really application level because there's no user interaction, no direct user interaction. But what Jam does is it will associate a token balance with a service. So services hold tokens. They can not any token, the specific token of the Jam chain, DOT, but while they're agnostic to things like governance and staking, they're not agnostic to the token. The token is a first-class piece of functionality. What this means is there's an opportunity for it to be used. The economics of this token, because it's impossible to, well, it's not impossible. There's always hard forking, but it's not so easy to upgrade the Jam chain. It becomes possible to credibly fix certain economic elements of this token. It's not possible on a purely upgradable chain such as the Polkadot relay chain because, well, you can arbitrarily, if you want to, just double the issuance and hand it to whoever you want. If you can control the outcome of a particular vote in governance, you can do that. Nothing can stop you doing that. Essentially, economics is subservient to governance. Now, this may be a sensible thing. It may be a reasonable policy, but the point is that the relay chain cannot disallow this as a policy. It's de facto the policy. It's the only policy that it supports. the Jam chain supports the possibility of having a policy whereby governance is not able to control the economics. And this is an interesting opportunity. Now, one of the things, I mentioned it yesterday for those who were there, one of the things that we're doing with Jam to try to ensure that Jam is sort of lives up to its initial expectations is to create a test rig for the Jam chain. And it's not one of these, little mini test nets running on questionable hardware that, keeps the cloud compute costs to a sensible level. This is a sort of fairly hefty investment. So there will be a Jam, call it toaster. So basically a test rig for full-scale trials and measurements of Jam. This is one of the things that held us back with development of the Polkadot relay chain, was the inability to actually work out what the emergent effects are, what the dynamics were of having a network at that scale. Right? The best we could really do was have a few dozen nodes on a test net, and then Kusama. But Kusama isn't great for monitoring because, of course, you can't look inside everybody's validator node, and a few nodes on a test net, which does give you this in-depth ability to investigate, isn't so useful because, well, you can't really simulate what it's like to have 1,000 nodes. This Jam toaster will be able to give us this level of research. We'll be able to create a network that is the full scale of Jam, which is to say 1,023 nodes, and it will allow us to investigate how the network actually runs at that level, and basically provide to you guys what precise performance characteristics you can expect for your parachains.
So Gav just talked about two things. First, about I think moving, moving economics downstream, or rather moving governance downstream of the economic policy. So it's no longer the case that governance will be able to decide some, properties or characteristics of the dot token economics, which fair, I guess. I think that anything having to do with economics actually links directly with the security of the protocol, and before we fiddle with them, making it harder to fiddle with them means that we think more deeply about their effects and sort of their consequences. Because if in this paradigm, if you were to try to change what is the, inflation rate of the protocol, it would require a hard fork fundamentally. It's not going to be, we just do a runtime upgrade and everybody's happy and all the parameters are changed. No, it's going to have to require validators to coordinate and effect this change and choose the chain in which we fix this, the certain parameters, which I kind of agree with that. Yes, making things just a little bit harder to change. It's not entirely impossible. You can always still fork the chain, but makes us think very deeply, will necessitate for more deeper research, not just having things be changed willy-nilly, because like Kian said, having an upgradable blockchain has actually spoiled a lot of people, and we just do things at this point at any time. But instead, sort of making it harder will definitely ensure that we are taking, we ask ourselves all of the right questions before we make these things happen. And then, of course, the Jam toaster. Now, I am very kind of on the fence about this because I don't think it's the case you want to have a single super node, stack. I think you actually want to have a distributed system if you really want to simulate a distributed network. Otherwise, it's a case of it works on my machine, and sort of reflective of what would happen in a decentralized network. So there's that. But it's Gav. He has plans to have a supercomputer in the backyard. Let's just let him. Good things can only come out of it.
So let's talk. I'm a bit over time, but I've only got 10 more minutes, so I'm just going to push through. I want to talk a little bit about jam and substrate, how substrate and jam are going to interact. This is the asterisk bit, right? This is the bit where it's like actually relevant, so you can sort of prick your ears and listen. All right. So the first thing, mentioned it in passing, benchmarks are optional. What do I mean by optional? Well, it's not that that no one will ever need to do benchmarks again, but the most of the time that you need to do benchmarks, that need will be averted with the jam chain. Why? Because jam is fundamentally a metered system, which means you can check to see how much work you've done after you've done it. You can also game theoretically sort of limit how much computation is done. This, I say sort of game theoretically because it's not something that you would do inside of the parachain itself. You would rather do it at block construction time, and you would just throw out a block that used more gas than it was meant to use. For what it's worth, I use gas when I talk about metered time and weight when I talk about benchmarked time. There may be instances where you still want to do benchmarking, essentially where the metering, which isn't necessarily going to be quite conservative for the PVM, like, we have to meter for worst case to make it secure. When that metering is a little too conservative for your use case and you want to eke out an extra 20 or 30% performance, say, maybe, whatever those numbers are. Hopefully it'll only be 5 or 10%. Then there's also the possibility that you might want to benchmark something when it can execute for a really long time, and you want to make sure, and it's up to the user parameters that will determine how long it executes for, and you want to make sure that it doesn't execute. It's not going to execute for that long. Yeah. All right. Next thing, XCMP. So jam, as I mentioned before, it requires full XCMP. Why? Well, because we kind of fudge things a bit in the relay chain. We allow more data to be passed in via a candidate receipt than would make sense if all parachain passed in all of that data all of the time. Jam has, being more general purpose, is more rules abiding. Right? It has rules that it expects all services to follow, even the parachain service. And part of those rules are this, as I mentioned early on, this limit as to how much information can be passed from refine into accumulate. And that effectively dictates how much the upward message queue can pass. Essentially, how big those messages can be that go through the relay chain. At the moment with HRMP, all of the messages go through the relay chain, and therefore all of the messages a parachain would have to send would have to fit into this 4 kilobytes or whatever. Probably not that realistic, and therefore XCMP, where in fact you only pass the message heads and the actual message data is sent off chain, would be the obvious and much needed fix. Accords. So I've talked about spree a little bit. I've talked about accords a little bit. So if you're not familiar, accords are these sort of encapsulations of state and logic, smart contracts, if you like, that have multiple instances, sit on each instance sitting next to a parachain, and they sort of send messages between themselves and allow for a parachain to do some synchronous interactions with them. They could be used for all sorts of things where there is no good trust relationship between parachains. For example, tokens. You might want to guarantee that a parachain will honor its side of the teleport when you receive a teleportation signal. At the moment, you need this reserve thing, right? Where you have a reserve and you send a message to the reserve, and then the reserve sends a message onwards to the actual destination. And it's a bit annoying for a few reasons. One of them is, of course, it's slower and more costly to have this extra chain involved. But a very important reason is that there's no trust relationship, or the trust relationship between the destination and the eventual and the source is broken by going through this third party. Yeah. But this means if you've been doing XCM coding, you'll have noticed the clear origin being inserted into some of your messages when you're using reserves. This is to reflect that lack of trust that the source and destination have between each other when the message goes via a third party. Well, with Accords, that wouldn't be needed, basically because they could teleport tokens directly between themselves. They wouldn't need the third-party reserve. But also, another accord could be an XCM forwarding accord that guarantees that even if a message comes via a third party, it is the same message that was sent originally by some source. And this means that you could essentially get rid of that clear origin, that annoying clear origin. The last thing I want to mention before we get onto the conclusion is one of the things I think is I get asked about occasionally. Jam, because it provides a much more general, less opinionated model for using these underlying cores, right? This underlying consensus, secure, resilient resource that the validators provide. It makes doing certain more exotic things like the usage of distributed availability for things like zero knowledge proofs. It makes it much more sensible and efficient. In particular, Jam enables this mixed resource consumption model. So a work package can utilize or can contain both work items that are, say, very heavy in terms of computation, but not so heavy in terms of the amount of data that they need to be made available, and other work items that come from services that are the opposite way around, right? That have lots and lots of data that they want to make available, but don't need to do much computation at all. So while the validators themselves are still have a very standardized sort of homogeneous requirements for things like bandwidth and computation, the services and the work that the services want to do in Refine can be very different. And by mixing and matching and putting together services that use a lot of one resource and not so much of another with their opposite counterparts, you can make much better use of the job that validators are doing. In essence, bringing down the cost, right? One of the more obvious ones is, utilizing distributed availability and maybe a little bit of snark verification stuff that requires relatively little computation, but a lot of the availability, and pairing that with, say, a parachain workload, which would use a lot of computation, but not necessarily so much of the availability.
I think this is also something that's worth mentioning, is that when we were working on Hyperbridge, we discovered that actually the limit to the amount of and because we had been testing async backing and everything, and we're trying to see if there was having 2-second block execution time would give us any kind of scalability boosts. And unfortunately, we found that it's the case that our blocks are not actually bounded by the amount of compute that they do. They're actually bounded by the data that's in the block. Because you can imagine, the Hyperbridge parachain is accepting a lot of state proofs. Consensus proofs are probably like 5% of the work that it does, and those don't really have huge data requirements, maybe unless of course Ethereum's full consensus protocol. But when we're accepting messages, right, messages is actually where Hyperbridge starts to make a lot of money, is that because it charges for people to pass messages around. And it's the case that the proofs for these messages are so huge that actually we run out of the 5 megabyte POV before we actually run out of the compute time. And this is very, very sad, of course, but you can imagine that if it's the case that in a single time slot that for instance a hyperbridge block is being processed on the relay chain, and that has a lot of data requirements, there's still actually some time to also process compute intensive applications. And I guess what Gav is describing here is that validators on a core will be able to mix and match different packages that require different resources, such that they can still continue to push out more attestations or more refined outputs than would have been possible without this sort of resource aware work allocation, is what I would call it, right? So this is also, like I said, just more looking at where we can tune and fine tune and eke out more scalability. Is that okay? If this work item requires more DA or more data, and then if this work item requires less data but more compute, we can actually do the same thing. We can actually put those work items in a same work package so that they can be executed on a single core, and that's also just like very genius in my opinion.
You drive down the costs for both. I've mentioned XCMP. I don't think I need to go into that again. So let's talk a little bit about how I see this unfolding. And obviously this is something that I've jotted down. I haven't thought too deeply about it, and I'm not. This is, after all, a fairly decentralized, quite chaotic process. So I don't want to. I don't want this brought up and used against me in 6 months, but I hope that it won't be too far off the mark. So we've already seen the preliminary RFCs, Sassafras, precursor to Safrol, and Corejam, precursor to Jam. These are the two sort of key technologies that are in there, along with PVM. These have already been, they're already sort of up. So the next sort of steps would be a draft of the proposal, which is coming soon. Some initial implementations. Notice I say the plural there. We would, once those are in place, open an RFC for discussing this and presumably making some changes. There are already question marks over points of the,
so I guess Gav was
design
just talking about
that I can't get into. I'm already
road to Jam here. I think we may have exhausted all of the sort of juicy bits of the Jam paradigm. Yep, I figured we'd exhausted most of the juicy bits. There's a question at the end about whether or not this is going to come to Kusama as well, and Gav says that of course yes, if Kusama the governance decides to implement this and accept this, then it will eventually. I just wanted to give some of my closing thoughts on this issue, on this Jam direction, and it's kind of what I've already said on stream so far, which is that the problem of scaling has haunted this industry since the very first blockchain, right, Bitcoin, which brought effectively a single-threaded application, right? In this kind of 10,000 feet view, it's Bitcoin is basically an application, application-specific blockchain, and it's incredibly single-threaded, right? Because you can't have multiple tasks running. There's just only a single chain, right? And then Ethereum generalized Bitcoin and sort of made it allowed blockchain to host multiple different applications. Of course, that brought some problems like state bloat, more problems like we need more or less wasteful consensus, right? Like because of proof of work, and they of course switched to proof of stake. But then very quickly we realized that having a single process, a single on-chain process, just still hurts our scalability like so bad, and there can be resource contention that drives the cost of executing programs on chain very, very high, unreasonably high, in fact. And of course, everyone in this industry agrees that there needs to be some kind of sharding, some sort of concurrent on-chain execution. Ethereum settled on what it called the roll-up centric roadmap, which is just basically allowing only two different kinds of sort of execution models to exist, which is either optimistic execution model or ZK, validity proof execution model, both of which have their problems. Like neither is perfect. And then we have Gav coming out and saying, well, we want to actually fix the issue. We want validity, like kind of like ZK, but we also don't want to have to do a lot of computation to get that validity, right? We want to be able to do just maybe a little bit of execution, and then have that execution be backed by high economic security of the relay chain. And then that was Polkadot version 1, right? This is Polkadot version 1. And, Gav is now taking it to the next level and saying, hey, look, the thing or rather, I guess, in terms of sort of abstract execution or abstract computation, Polkadot should not enforce that, oh, you only can host parachains, right? Gav is saying that actually we should be able to permit any sort of computation that exposes, sort of this service interface that he's described, refine, accumulate, on transfer, and of course, parachains fit very well into this model. But at the same time, different kinds of computation also fit into this model. You can also have smart contracts, actually, right? You can actually put a smart contract in here. But the only problem is that, of course, you would also have to bundle your own EVM execution or EVM executor into the service, if you just wanted to host a single smart contract. But of course, I can already guess that most people no one would really want to do this. But in general, this is super abstract, and you can really put any kind of computation in here. And not only are we going to allow you to put any kind of computation on the relay chain, in fact, we will make it multi-core and friendly, parallelization friendly, so that you can pause execution and it can be executed over multiple blocks, potentially over multiple cores. Workloads can be shared on a single core, depending on what kind of resources they're consuming. In fact, it's the case that multiple work items, as long as they don't consume the entire resources for that core, can sort of be shared on a single core, and that can allow for things like synchronous composition, as well as of course, this scales the number of cores that the relay chain can provide. Now, all of this stuff is exciting. All of this stuff, I think, is going to contribute significantly to bringing more developers on chain, allowing more users also interact on chain. I think Gav has chosen the direction of cloud provider fundamentally, right? Polkadot basically becomes the AWS or the GCP, what have you, of blockchain, and just provides, all it does is provide, trustless compute. And in my opinion, in this new brave new world, it actually wouldn't really matter what chains applications are hosted on, right? Like, in a world where block space is kind of abundant, it's no longer the case that anyone would really care where an application is hosted, or your application is hosted on Ethereum, or your application is hosted on Near or whatever. It's now going to matter how fast these applications are, how many users they can handle, and how well connected that they are, right? Like, I believe that secure interoperability, especially between multiple chains, blockchains themselves, as things that are sort of at the top of our minds, will fade into the background. No one will be thinking about chains anymore. People will be thinking about the applications themselves, and sort of, like I said, these already these criteria for them, and can they handle me? Can they handle my demand right now? Is it the case that they're reliable as well? Is it the case that they spike when there's a lot of people on them, or not? Is it the case that they are sort of, they provide fast finality for my actions, for my interactions. If I'm having to wait 7 days, 1 hour to get things confirmed, that's not a great user experience, right? Polkadot provides instant finality for all applications that are hosted on Polkadot, and I think that that's going to set Polkadot apart from its competition. And that's just basically my sort of closing thoughts on this issue. David, if you have anything, please let us know.
Oh yeah. So like I think this jam chain is going to like create the .com bubble moment for like blockchains, because this jam chain becomes like a generalized like distributed platform where you can host really any kind of application. It doesn't have to be a blockchain, it doesn't have to be a parachain or a rollup or a smart contract. Anything that can execute within like the interfaces that have been designed by the system can virtually be hosted. You can host applications that just maybe they only exist for a month in blockchain, and that's all. As long as like it's just providing the first distributed platform that is also verifiable. So if you want to do anything that is verifiable, basically, you can just host it here. And I can see that it will create a lot of like innovation, and we'll see like new kind of applications that we have never actually thought of before. People start like deploying those kind of applications. It seems like the same way how cloud functions like in the early days when they just boosted like people building web apps up and down. So it will be the same like effect this will have for like distributed computing. So I think like this like the like the final like or the beginning of the new paradigm for like blockchain, Web3, and distributed computing. So
I couldn't have said it better. All right, guys, this is it's been a fun stream. I think we're already at the almost 3 hour mark. But I'm still going, man. Like nothing stops the stream. But it's time to go now. So I will see you all in the next stream, and don't worry, Hyperbridge is coming. We'll see you guys soon. Bye.